If you're a ceramist, you know the feeling. What happens inside that kiln can sometimes feel like, I don't know, magic, or maybe just a complete mystery. But what if you had a map, a guide that could actually tell you how your materials are going to behave at any temperature? Well, that's exactly what a phase diagram is. It's your roadmap to a perfect melt. So here's how we're going to break it down. We'll start with those common ceramic mysteries that drive us all crazy. Then I'll introduce you to your new best friend, the phase diagram. We're going to learn how to read its key landmarks, apply it to real-world glaze design, and then lock in a practical workflow you can actually use. And at the end, we'll take a quick peek at the future of all this stuff. All right, let's just start with a feeling we all know too well. You spent hours, maybe days, on a piece. The form is perfect, but then it comes out of the kiln and the glaze is crazed, or it ran all over the kiln shelf, or, it's just this dry, under-fired mess. That frustration of endless trial and error, that's what we want to get past. Because this is what we're all shooting for, right? A perfect, predictable melt, a glaze that flows just enough to create this beautiful, strong glass, perfectly fused to the clay. It's really the difference between a happy accident and intentional, repeatable mastery. So that's the million-dollar question, isn't it? How do we actually get that control? How do we go from just blindly following recipes to truly understanding and designing our glazes? Well, the answer lies in this incredibly powerful tool. It's time to introduce the phase diagram. This is our ticket to moving beyond just hoping a recipe works to making intentional, smart decisions about our materials from the very beginning. To put it simply, a phase diagram is a graph. It's a map that shows you if your material is going to be solid, liquid, or some mix of both at different temperatures and with different recipes. And look, this isn't just for scientists in a lab. It is one of the most practical tools you can have for predicting what's actually going to happen inside your kiln. Now, I know what you're thinking when you see this. It looks incredibly complicated, right? And yeah, they can be. But here's the secret. You don't need to understand every single line and region. We're just going to learn how to spot the most important signposts that matter for a ceramist. So let's get practical and actually learn to read this map. We're going to focus on the single most important landmark for any of us, finding the melt zone. And that usually means finding something called the eutectic shortcut. Let's start with two of the biggest players in any studio, alumina and silica. Now, on their own, their melting points are just insanely high. Alumina won't melt until 2050 degrees Celsius. Silica is not much better at 1723. I mean, that is way hotter than most of our kilns can even dream of reaching. But what happens when we start mixing them? This right here is the phase diagram for alumina and silica. So that up and down axis, that's temperature, going from low to high. And the one running side to side, that's our composition, our recipe, going from 100% silica on one side to 100% alumina on the other. And this quote from the research really nails why we care about this. It says, our goal is to form a liquid, a melt, at a lower temperature. That liquid is the magic glue. It helps everything fuse together, making our glazes and our clay bodies strong and dense. Now, look for the lowest point in this big V shape, this valley on the diagram. That is our key landmark. That's the eutectic point. It represents the one specific mix of alumina and silica that has the absolute lowest melting temperature possible. It is the sweet spot. It's our shortcut to getting a melt. And get a load of that temperature, 1542 degrees Celsius. That's hundreds of degrees lower than either pure silica or pure alumina. That's not just a small tweak, that is the chemical magic that makes modern ceramics possible. So the big takeaway is, mixing materials together can dramatically drop their melting point. Okay, so let's bring this into the real world. In glaze design, we're not just mixing two things. We're using fluxes, things like sodium, potassium, or calcium oxides to push that melting temperature even lower. But here's the thing. It's always an art of the trade-off. This table lays out those decisions perfectly. You want a lower melting temperature? Okay, add more flux, like sodium oxide. But you have to be careful. That often increases thermal expansion, and that's what leads to crazing. Ever wonder why a glaze works on one clay but not another? This is often why. Want to make your glaze tougher and stop it from running down the pot? Add more alumina. But guess what? That's going to raise your melting temperature. You see, every choice has a consequence. And you can use this knowledge to create really specific effects. Let's talk about a matte glaze, that beautiful, soft, non-glossy surface. It's not an accident. It's made by intentionally growing tons of tiny little crystals inside the glaze as it cools. So by adding things like calcium oxide, we can encourage crystals like anorthite to form, which breaks up that glossy surface. This is design, not a firing flaw. So the big question is, how do you actually put all this together in your own studio? Let's talk about an intelligent, repeatable process that takes you from looking at a diagram right to loading your kiln. Okay, here's your 4-step game plan. First, you start with a phase diagram to get your intuition. Let it point you in the right direction. Second, you run small, targeted test tiles. No more random guessing. Third, you actually measure the results. How's the gloss? Does the glaze even fit the clay? Is the clay body vitrified? And fourth, based on what you actually see, you iterate. You make your next change intelligently. And here's why this matters so much. This whole process, it transforms your work. You stop being just a recipe follower, hoping for the best, and you become a designer who makes informed decisions to get exactly the results you want. And believe it or not, this is just the beginning. The same principles we just learned by reading these simple maps, they can be applied on a much bigger scale, all thanks to a technology called CALPHAD. Think of CALPHAD as a super-powered phase diagram calculator. It takes all the ideas we just talked about and uses serious computing power to predict exactly what will happen in super complex recipes with tons and tons of different ingredients. Just like this quote says, CALPHAD lets scientists and engineers pull together all the data we have from real-world experiments, from theory, and use it to design totally new materials from the ground up, all without having to run thousands of physical tests. It really is the next level of intentional design. So, we've looked at the roadmap. We've learned how to spot the key landmarks, and we've charted a course for intentional design. The map is officially in your hands now, so the only question left is, where are you going to explore first?